we're going to do an exercise out of the Wizard book, or Structure and Interpretation of Computer Programs. Hoping to do a couple videos around SICP coming up. And we're going to start each video by a mathematical understanding of the exercise. So we're actually going to address everything going on in the book on paper with not an actual computer language, strictly mathematical language. Then we're going to dive into Clojure and then Java and then Scala with this one. Trying to do SICP exercises in multiple languages. So this is square roots by Newton's method. It's in the first part of the first chapter of Structure and Interpretation of Computer Programs. And the idea is you need to get a function alpha. What alpha does is it takes an x and maps it to its square root, the square root of x. And we're going to consider this. What's important to us is from the positive reals into the positive reals. And of course, for the square root of x, to say that square root of x equals y is to say that y squared equals x. And really, the way we do this is because as you know, many square roots end up being irrational, and you can only approximate them. So we're going to have a guess g. So really, we're going to be working with not just the single x and square root of x, but this tuple x comma g, which is in the positive reals cross the positive reals. That's a Cartesian product containing, it's basically all the ordered pairs of real numbers. And another way to write this is as your positive real sign, then you say 2. It's as if r squared, r cross r. And we just call this r2. And what this tuple xg is going to mean is basically going to mean that g is an approximation of the square root of x. So with that said, what we're really doing, we're going to rewrite our function alpha as alpha is defined as x comma g mapping to x square root of x. It's a function that really goes from positive r2 to positive r2. And how do we do this? Now you've seen that we've just basically explained what this function is, what it does. We can see what its inputs are and its outputs. What we can't see is how it actually does that, which is the important part. A lot of times in logic and in math, you deal with essentially what functions as black boxes. They call them black boxes because you can't see inside them. It's a box, you can't see inside of it, but it has an arrow going into it, an arrow going out of it. So if you think of a function as a machine, little objects like x's go in on these conveyor belts, and whatever happens in here, who knows what, out comes this thing, square root of x. And you can solve problems with black box abstraction by starting with your inputs and your outputs. I don't know anything about alpha except that I know its input and its output. And that's just the place to start. From there, you actually have to do the work. And what's going to happen here is if we have this machine called alpha, and you put x in it, and you get square root of x, which is approximately this g thing or we could call it alpha of x. The G is for guess, by the way. But what we're going to do is we're going to peek inside of this. We're going to break this open. We're going to look inside this box, and what are we going to find? What we find is happens a lot when you break open these boxes is we put X in there, and it goes inside here, and inside these boxes are more. They're little boxes. There's little boxes inside. So let's call it beta going into gamma going into delta. So there's these little boxes. Inside alpha is a chain of smaller boxes. Out comes alpha of x. Oops. Alpha of x. So this chain, what this chain is, this chain of boxes is function composition. We have what happens here. What happens to x is it goes into this big chain of functions. See here. Equals alpha of x. So delta of gamma of beta of x equals alpha of x, and all this means is that alpha compose gamma compose beta equals alpha. So this is, of course, function composition. Many of you may have seen in like high school math classes dealing with function composition. It's usually F and G, and what you'll notice is something that might be a little bit counterintuitive is how we think of left and right in mathematics or in English, because mathematical statements are often read left to right, but if you remember correctly, when you're composing, you always evaluate the part on the right first. You evaluate the right stuff, and then you evaluate successively toward the left and the leftmost is the one that you evaluate. And you can see this reflected in the way we set up our chain of machines. By it goes into beta first, then into gamma, then into delta, and then finally out. But when you're setting up your chain of arrows and machines, you're always doing it. It looks like a reverse order from when you're doing it with the application notated this way. So now what do we have? Well, we used to have one box that we didn't know anything about. Now we have three boxes, but we still don't know anything about them. The only thing we do is that the order in which they're chained together, and we have that when chained together in that order, they come out to the same thing as this alpha thing. This alpha thing, which gives us a tuple containing a number and its square root. So we're going to take this chain and we're going to really unpack it, because we're going to define every single one of them. All three of these functions have to be defined just like we defined alpha, and that should bring us closer to really understanding this procedure. And again, this is all in the first part of Chapter 1 of Structure and Interpretation of Computer Programs, also known as SICP, also known as the Wizard Book. And what the authors do is they write it directly into Lisp. It's in a very old Lisp called Scheme. They sort of substitute this language Lisp for like a pure mathematics language that you would see on a blackboard. again, what I'm doing is I'm doing it strictly on paper. Then we're going to jump into some programming languages, and we're not doing the old scheme from the book. We're actually going to translate these situations into slightly newer languages. So we got to get this beta going. By the way, I'm sorry. I'm using the Greek alphabet here, and I just want to. You can skip ahead about 15 seconds if you know your Greek alphabet, but I just want to put this here for the people who don't know it. The alpha, so this is alpha, beta, gamma, and delta. That's I think that's everything. Of course, writing functions this way requires a certain math background. It doesn't require this certain math background. I shouldn't say that, but it's more common in advanced math and very like formal pure math or logic. A lot of like linear algebra professors won't even notate it this specifically, but I hope you can follow along. I'll explain again the parts. It goes your input item. In this case, it's a tuple, and it maps to the output. And the output of beta is a tuple returning x, never changing it, and it performs some arithmetic on G and replaces G with that. So if you're thinking Java, mutable data, just reassigning a value to a variable. If you're thinking immutable data, you're not renaming G, but you're passing G through a recursive call to get the same effect. And we're gonna talk more about that because right after I finish this, I'm gonna compare a Clojure implementation to a Java implementation. But anyway, back to the function. This is beta is defined as a function taking xg tuple, mapping it to x. And replacing G with 1/2 times the quantity x plus x over G. And this, the source of this, or the domain, as it's called, the source of this function is R2, the set of all real numbered two tuples. And the target, or the range, is also R2. So just again, just notationally, skip ahead 15 seconds if you're comfortable with this. We say this notation works: name, input, output, source or domain, and target, otherwise known as range. So this is what the notation refers to. This is the parts of the notation. Didn't want to skip over that if anybody wasn't comfortable with that. So, but it's just that out of the way. Let me just delete these, and I think everyone's okay with the Greek alphabet by now as well. So we'll delete those and onward. So we have beta. This is what our beta is going to look like, and it shows us pretty specifically. It gives us real math to do. Like we can evaluate this arithmetic with what we know about our real numbers, the types of our inputs and outputs. So moving forward, the next function we have to define is, if you remember in the chain, after it comes out of beta, it goes into gamma. Gamma, taking this pair xg, mapping it to, and here we're going to go into conditional. This is sometimes how you might see a conditional situation notated in mathematics. We're going to return simply the tuple xg, comma 1. So we're going to be in R3 here. No, I'm sorry. Excuse me. Not R3, but I'll write that when I get there. So it's not going to change it and going to append a 1 to it if this value, let me just write it, is less than p. And what this means is the absolute value of g squared minus x, the absolute value of this quantity is less than this number p. And I'm going to write this later, but p is going to be a constant, and it's going to be a constant to measure our precision. So if you're reading along in the book, this is what's referred to as the good enough part of the procedure. They define a scheme function called good enough with a question mark. Else. Then it maps to xg0 else. This function takes from R2 and places it in. What this is it's R2 cross the set containing 0 and 1. So this is how we're representing our 3 tuple. Look what I actually no wait that actually looks pretty good. Let me just put it down a little bit. Our 3 tuple, our range when we're returning a 3 tuple looks like this, and just skipping ahead, we use 0 and 1 to represent Boolean information. So this is standing in for what's eventually going to amount to true and false in our code's conditionals when we implement. So with beta and gamma, let's just make delta. Delta is a function mapping. This is going to be 3 tuple xgb, mapping it to, again, conditional, where it just returns xg and we're done. If b is set to 1, and what it does is it returns beta xg else. You could say else here. Really, what that means, because there's only going to be 2 choices if b is 0, and to the surprise of I hope no one, we have look what I did. Let's be consistent. The positive R2 cross 0, 1. So that's what B represents, is that value that's in 0, 1, into a range of R2. Bingo, we have our 3 functions. Let me zoom out a little bit so we can see a little better. There's our beta, our gamma. It's a little. There's a bunch of stuff going on here, but all the information you need is here. All the information you need is here. Just let me space it out a bit so it's a little bit more readable. And if you remember, remember our composition down here, it's going to go into beta first, then into gamma, then into delta, or it's gonna look like this. And we have this composition. delta compose gamma compose beta. And basically what this function looks like, remember the outcome of this composition operation is a function in itself. This is going to be from the, what it does is it takes, if this is our set, our domain set, our original input set, we'll call it the source of beta. It takes a bunch of objects to the target of beta. But the important thing to note here is that this is the condition of composition. This is what makes a composition legal. Is if I can compose, if I can do gamma compose beta like this, I can only do that if target of beta equals the source of gamma. And as we keep going, this is going to keep going. There would be many, many more arrows here. I'm not going to try to draw the arrows. I'm just saying this is where the arrows go from the set. The arrows go between the sets, and they can hop into different sets when you have a just in a succession like this, when you have function composition. And this is the target of alpha, but what I'm claiming is that this is a legal composition. It's a valid composition. I'm claiming that. In order for me to claim that, I should point out that the target of gamma is equal to the source of delta. They are the same set. And it finally lands in target of delta. I'm using source without vowels, and I'm using target without vowels. This could be, some people prefer domain. So I'm saying source interchangeably with domain. I'm saying target interchangeably with range. Just to be clear, I don't want to leave anyone behind here. And so in order for me to, so let's check this. Target of beta equals source of gamma, right? So I have target of beta, that's this part of the function notation, equals the source of gamma. Gamma, here's where the source is. It's on this side of the arrow. So look, target of beta is positive R2. Source of gamma is positive R2. Bam! We got it. Now, if you look at this next condition, target of gamma has to be equal to the source of delta. They have to be the exact same set. So let's look. Here's gamma. The target is to the right of the arrow here. So yeah, the target is positive R2 cross 0, 1. That's equal to what? Equal to source of delta? Exactly. Positive R2 cross 0, 1. This set, and this set are equal. These are completely equal, completely interchangeable, just like this set and this set. So since those equalities hold, this is a completely valid composition, a completely legal composition. And it's totally gonna work. And we can shorten this. It's sometimes annoying to see these different boxes, and this is different boxes and jumping different arrows, hopping across like Frogger. Instead, we're going to just rewrite it. If we remember that this chain of compositions, we can name it alpha. Alpha is just the name of this chain, and this is going to be one just set of arrows from really the source of beta into the target of delta. Another name for this, it's the exact same thing, but a slightly different name, is source alpha and target alpha. And there we have it. There is our complete function composition. It's we can see it's valid because all the types line up in the right places at the right times. This is how we're going to find the square root. We have a procedure to find a square root. Now, I didn't explain much of this in natural language, exactly why this amounts to the square root, but we're going to see it happen. So if you haven't seen the chapter, you should go read the book. It's a great book. They explain in great detail, and we're going to, when I come back, we're going to implement this in Clojure, and our Clojure implementation is going to look a lot like the scheme implementation. But the point is, this is function composition, and Lisps are the best languages for function composition, as everybody knows. And then we're going to compare it to Java, see how mutable data changes it, because that's one of the great things about like self-referential calls to composed functions, is that you can do this type of stuff with immutable data, with variables that don't change their value throughout their lifetime. So thanks for watching. Check out the Clojure video and stay tuned for what's next, one step at a time.